title, but given that you guys are the expert, I sort of tried to think about what niche I could occupy that you don't already occupy. So I'm going to talk about rainfall runoff in urban areas, and my experience of it anyway. And I was going to say a few things. Maybe discuss a bit how does urban surfaces influence rainfall runoff processes. I'm thinking on a larger scale. I'm thinking catchment scale here, more than street scale perhaps. So larger catchment. Having thought about this and being pushed by people using these Flood Estimation Handbook methods, what were the attempts we made to try to implement some effects of urbanization on specifically flood runoff, and how that evolved over time, and how I think this is evolving into what I'm getting more and more interested in is green and blue infrastructure in urban areas. So that's the sort of three themes I wanted to talk about. So I guess for most of you here, this is basic information. You have a catchment in a natural, semi-natural state, and it rains on it, and some of it gets intercepted in the trees, some of it evaporates there, some of it, a large proportion of it will infiltrate into the soil because there's nothing restricting infiltration there, and there'll be some runoff. And somebody comes along, built a city on top of it, put some impervious surfaces up, some roofs, some roads, etc. The amount of rain is the same, but now we're restricting infiltration, the natural infiltration into the soil, so the infiltration arrow becomes smaller, which means that where does that water go? Well, it becomes runoff. And typically, if you read the literature, what you see is that we increase the volume then, so less infiltration, more runoff volume goes up. So here's the blue, that's the natural response, the same blue line, but now this is the response from the urban catchment, is this red dotted line. The volume should have increased, but also the timing of it should have decreased. So the lag times become shorter. The water suddenly finds its way into more efficient sewer systems, drainage systems. It should speed up the response time. So if you're standing at the outlet of the catchment and all the water is funneled into drainage systems specifically designed to speed up drainage of urban areas, you see a faster response. I think these are reasonably well established results in the literature that that's how urbanization in general affected. Of course, the idea of the green and blue infrastructure is then that you come, instead of having this sort of brutalist architecture here, you try to put some greening stuff in to try to engineer it back to a semi-natural state, so trees, green roofs, green walls, ponds, whatever you can think of to try to encourage that natural increase the infiltration rates, and therefore engineer the runoff arrow back to something that mimics the original response, even though we might not get there. Yeah. So this is trying to schematicize that by the green. Even if we might not get there, we get some of the way towards what it used to be. And of course, this is important it's important if you're considering flood risk downstream of here, but it's also important for the receiving waters that they don't suddenly get very altered ecosystems, etc. So I think there is a good case for studying rainfall runoff methods and the impact of urbanization. So just a bit of historical context. Albert alluded to it. In my previous life, I was a hydrologist at the UK Centre for Ecology and Hydrology, and I was hired there pretty fresh out of my PhD, and I was given this amazing opportunity to work on the updates of what was known as the Flood Estimation Handbook. And one of the major outputs of that was something that was called the revitalized FSR-FEH rainfall runoff methods, REF-H methods. So this was an old rainfall runoff based approach that was used by all consultants in the UK to estimate, design hydrographs, or how big is a 100-year flood, etc. So we spent, well, I'd say I spent about 3 or 4 or 5, I can't remember. Yeah, since 2003 to 7, 4 years, trying to develop this method and disseminating it. This was in a, you can tell it's quite a long time ago, because it's based on an analysis of 1,200 events. So I analyzed 1,200 individual flood events, almost by hand. I think you read papers today, people use machine learning stuff, and they got hundreds of thousands of events. So just tells you a bit about how old I am. The thing was, though, that very few of these catchments were urban, because we didn't have very good quality data from very many urban areas. It seemed like nobody was bothered really monitoring the runoff from highly urbanized catchments. So all this was developed, this system, this hydrological model, but it didn't really consider urbanization very specifically. So here's a schematic of the model. It's a standard event-based model. You have some rainfall, the total rainfall, it rains in the catchment. A certain percentage of that is lost, gets infiltrated in the soil or stuck in the trees or whatever happens to it. So you say it rains 100 millimeters, percentage runoff of 50%, well 50%, 50 millimeters of the rain turns into runoff. You then route that to the outlet of your catchment using a unit hydrograph approach, and you add some base flow at the end of it. And this is kind of what it looks like. Here's the rainfall, total rainfall, the effective rainfall, and this is the hydrograph response you get for this particular catchment. It has a few model parameters. It has Cmax, that's the typical depth of the soil. Tells you something about how much water the soil can hold. It's got time to peak, how fast is the catchment. It's got something about initial soil moisture, how wet is the catchment when the flooding event starts, and something about base flow. In the first iteration of this model that we produced, urbanization only came through in one of the parameters, which was the time to peak. Some time to peak for the catchment is decided by some descriptors of the catchment. It relates to how wet it is, how long the river is, how urban the catchment is, and how steep the catchment is. That's what decided how quickly it responded. But this was the only place at all in this whole model that urbanization appeared. And I just want to say a bit about these data. So this was meant to be a model that could be applied anywhere. In any catchment in the UK. So it's based on the UK CEH's land cover maps. So we try to tease out of the land cover maps how urban a catchment is. Now what you need to know about these land cover maps is that they are designed for people to say something about what goes on in the countryside. They are really there to inform farming policy, farming practice, etc. So there's something like 50 or 60 classes of land use in there, and you can see them, some of them over here. Improved grassland, neutral grassland, acid grassland, blah, blah, very detailed stuff, except when it comes to the urban and the urban areas, because they weren't interested in that when they developed these maps, because that has no implication on farming policy. So they went with urban and suburban. That's the only two ways this land cover map classifies urbanization. Nothing about connectivity, existence of sewer system, none of that. It's just whether it's sort of dense central urban area or a suburban area. That's all we know about it. So we were trying to build a model that could respond to urbanization based on whether things were urban or suburban. So once the model was released, there was I think the user community was reasonably happy. It was easy to use. It was, as followed up by some tools that made it easier to use, but the effect of urbanization was not really in there, and that was a criticism. So the first thing to do after the release was to try to rectify some of this, to try to put urbanization in there. So this was my first attempt. I can't remember, this must have been a few years after. And the first attempt of trying to put urbanization in was simply to say, based on these land cover maps, I tried to work out what the fraction of the catchment that's covered by urban area what's and anything else. I then take those urban and suburban classes and do some very high-level approximation as to how much of an urban area is impervious. If you say is impervious area, it turns out that there's some ballpark figures that said 30% of the urban area is impervious, and some figures taken from the drainage community that says, well, you have an impervious area, then probably the percentage runoff is about 70%. 70% of the rainfall gets turned into runoff on an impervious area. Obviously, these are quite, guidance ballpark figures. So the first attempt was simply just to say, okay, I split the catchment into impervious and non-impervious area. I assign different percentage runoff to the rural area, and I assign 70% to the impervious area. And that's it. Off we go, and I did some testing and calibration and validation, and that seemed to improve the model performance on reasonably highly. The original model improved the performance on highly urbanized catchments. But there was I thought there were some flaws in this, in that I now have split the catchment into impervious and non-impervious. I've generated effective rainfall in each of these parts of the catchment, yet when it came to the routing bit, I just merged it all together. So I went one step further and I tried to develop several routing models for the urban impervious bit and the non-impervious bit of the catchments, assigned different unit hydrographs to them and tried to calibrate. And that was reasonably successful, and that became what effectively was called the second version of the RefH model, which became implemented in industry software. And this is the sort of effect you can see. So now we've got percentage runoff being worked out on urban and suburban area, and they get routed separately to the catchment outlet where they get combined. So we've got situations like this where we have a rainfall event, storm event of some sort. And the black line here would be the default response if this catchment didn't have any urban area at all. And then I think we increased it by, I can't remember the percentage increase of impervious area in the catchment, but you can see that the model responds by decreasing the response time. So the more impervious area there is, the quicker the catchment responds, and the volume, the area under the curves increase as well, so the volume goes up. So it responds in the way it should. Now, that is obviously quite simple, quite simple approaches where we use this percentage runoff concept for the impervious areas and just assumed it was 70%. But actually, we had PhD students and projects looking into, is that actually true? Well, how is this number just fixed, 70%? And if you look into the literature, and here's an example of some studies that have looked into generation of runoff in urban areas. And people look at roads, pavements, roofs, urban areas in general. And one of the striking things is that when people actually start monitoring what actually goes on, several of these studies would report variation in runoff rates across seasons. So in summer, the runoff from the impervious areas is less than the runoff rates in winter. Now, why would that be? Well, my my sense was, okay, these impervious areas are probably seemingly impervious, but not really. There must be some connection to the soil moisture underneath. There must be some dynamic here that we're not capturing by just imposing a blanket percentage runoff. I mean, full kudos to the people who've done field studies in urban areas. It's definitely not easy to be out there. It's all sorts of challenging monitoring the urban environment. So people tend to do lab experiments, but they're much more well confined and it's easier. But does that actually represent all the fluxes? So I think this is an interesting area, but I think it's very difficult. But the takeaway was that this seems more complex than just imposing a blanket percentage runoff here. So together with a PhD student, we came up with we said, well, let's try to take these ideas of splitting the catchment into impervious and non-impervious, but try to see if we could develop a system where we could be a bit more physics-based. So we took a conceptual rainfall runoff model, which was called DAMOD, and this DAMOD model had a long history because it was part of developing this RefH model. So this is a continuous rainfall runoff model. Unlike the RefH model that just gives an individual event, you give this one a time series of rainfall and evaporation, and it can simulate a time series of runoff. So rather than take this sort of brute force approach and say the percentage runoff is 70%, we thought, well, actually what's happening in the field is that these impervious surfaces are restricting infiltration there. So why don't we move away from percentage runoff, which is just a sort of summary of what happens, to actually look at what happens at infiltration. So we did the same sort of thing. We started by looking at infiltration into the soil. So remember, these are lumped catchment models, so we're considering the whole catchment as one. The infiltration, which is F, is now a weighted average here. So this is supposed to be green and grey. This line up here, so we've got something like some green areas, some impervious areas. So we get infiltration in the urban areas. So I is the rainfall intensity, U is the fraction of the catchment that's covered by impervious area, and that's the infiltration in the urban area. Similarly, 1 minus U is then the fraction that is non-impervious. It's the same rainfall, but now we're looking at an infiltration model into the natural infiltration into the soil. And for this natural infiltration, we use the probability distributed model. This is the CEH standard model, which says that the infiltration, this is an important point, the infiltration into a natural soil relates to M over S. So S is the capacity, field is the capacity of the soil. So this is the volume of water you can have in the soil. M is the actual water in the soil. So if M over S is close to 1, which means the soil is very wet, it's full of water. If M over S is very small, that means the soil is very dry. There's plenty of opportunity for the soil to infiltrate more water in there. So that bit goes up there, and then we're left with this bit here, which is, so how do we describe infiltration into the urban area? And we came up with 2 ways of doing this. One where we have a fixed percentage runoff. So that's a bit like saying 70% of the rainfall is automatically turned into runoff in an urban area. Or one that says down here, so this is model 1, it's a fixed percentage runoff. Or one here that's more dynamic, that says there's a certain fraction of the natural infiltration. So 1 minus gamma here. If gamma is 0, that means the urban area, this term becomes 1, and the urban area infiltrates in exactly the same way as a rural area. If gamma is equal to 1, then this term is 0, and there's no infiltration in the urban area, or the impervious area, so it's completely sealed off. So gamma here is a parameter that sort of says how restrictive is infiltration on impervious areas. And if so, there's some. So in order to what we're trying to do is trying to figure out which one of these two models will perform best. And there were some theoretical considerations. So here's a graph that shows you the saturation. So this is M over S. So this is how wet the soil is. Here we've got a completely dry soil. And over here we've got a completely saturated soil. And up here we've got how much of the rainfall is infiltrating into the soil. So the grey curve here is the rural, the non-urban areas. If the soil is completely dry at this point and it starts raining, well, there's plenty of space, so 100% of the rainfall just disappears into the catchment. You don't see runoff from a very dry catchment. As the soil starts to become more and more wet, the infiltration sort of tailors off. And when the catchment if the soil is already saturated with water, we can't physically stuff any more in, and there has to be runoff, which means the infiltration is zero. So that's the rural model. Urban model 1 says there's a fixed percentage of the rainfall that turns into runoff. It's 70%, which means at all times must it be 30% of the water. Yeah, where's the rest going to go? If 70% is runoff, 30% must go into my soil. So but it doesn't matter what the soil moisture is. It's just 30% all the way up to here, where it meets the rural curve. At this point, it turns out that the soil is so wet that having no urbanization would generate more runoff than if I just continued out here with this naive approach. So our urban model 1 goes up to this point where it meets the rural, and then everything is so wet at this point that it just acts as a natural catchment. Urban model 2 is the scale version, so it looks a bit like that one, but it sort of scales more naturally down to 1. So this is two. It looks minor, I think, but I think there's some important implications when you're trying to do this more physically. So we want to assess the performance of this model, and to do this we found some, I think it's 28 catchments in the Thames Basin of varying degrees of urbanization. Each one of them have rainfall and runoff data and hourly scale. We want to compare, so we want to calibrate the model, version 1 and 2, fixed versus dynamic infiltration on these models. So what we did was for each catchment we did what we call a jackknife calibration. So let's say we have from 1990 up to 2010, so what's that, 30 years of data? Is that right? 20 years of data, sorry. We divide that into 4 subsections of 5 years. So on the first iteration, we calibrate on the first 15 years, and then we validate on the last 5 years, and we calculate the net Sutcliffe efficiency on that. And we picked the first 10 years and the last 5 to calibrate the model and validate it on here, and so forth and so forth. And then we took an average of the model performance across these four areas. So we get one net Sutcliffe efficiency for the catchment, but it's an average of trying to do it over these subsets of data. The reason we did that will become, I'll get back to in a second. So we did that for both models, and then we thought, okay, well, let's just, how do we assess which one is best? Well, we look at the difference in that Sutcliffe efficiency. So we've got delta set there, that's the difference in that Sutcliffe. Well, it's the average net Sutcliffe of model 2 minus the average of Sutcliffe 1. So if that's a positive number, that means model 1 performs better, model 2 performs better than 1, and if it's a negative, model 1, which is the fixed one, will perform better than our dynamic one. And so we plotted this delta set, the difference in that Sutcliffe for these 28 catchment as a function of the degree of urbanization down here. So here we have the difference in model performance. If they perform equally good or bad, you would be on 0. Positive catchments where model 2 was better, are black, and the ones with model 1 are better, are triangles. And that's plotted against degree of urbanization. So down here, they're not very urban. There's a little bit of urbanization. Up here, they're very urban catchments. Up here. And you can see that a lot of black points, I think the majority of black points are above 0, so that's good. That's a fair bit of them are below 0, and they're quite below 0, which is not so good, I think, because that suggests that this fixed percentage runoff works better, which is slightly disappointing, given I thought we thought so hard about it. Now, the reason we did this jackknifing thing was because I was hoping that we could have done some sort of statistical t-tests and then say something about the statistical significance of the difference in the net subcliffs and work out the p-values and come up with some very scientific reasons why evidence for why one was better than the other. Turns out that didn't really work. Statistically, they weren't really. They look better, but statistically on a case-by-case, they probably aren't different enough to say that they're better. So instead, we invented a binomial test which says, well, if there's no difference between them, then there's a 50-50 chance of it being better or worse. So I just count the number of times it's better. And if that number of times it's better is a lot, there's more that are better than I would expect, and it was 50-50, well then possibly I have an argument to say, yes, these are small improvements, but there's a statistically significant number of them. And therefore, by looking across many catchments, I can say it is an improvement. There's a French team that followed this study, did the same sort of thing, just on a much bigger data set of French catchment data, and they came up with the same conclusion. They didn't use exactly the same rainfall runoff model, but essentially it was the same ideas. There. So I guess the conclusion here is yes, it pays. Overall, it pays. It's not big improvements, it's about 12%. The net subcliffe is on average 12% bigger when you implement the sort of a more dynamic implementation of infiltration than just a fixed runoff approach. So quite happy with that. Oh yes, I should say. So the previous graph. See if I can go back. Okay, here the results are plotted against how urban the catchment is, right? So how much urban land use there is. If you plot the same data, but now plot them against what's called BFI host. I don't know how familiar you are with these catchment descriptors. This is a UKCH descriptor. BFI host tells you something about how groundwater dominated the catchment is. Base flow index. So high values on the x-axis mean that these are very groundwater dominated catchments. Low values mean they're very flashy catchments with hardly any base flow in them at all. And here you see that the black points, there's always one, of course, but generally, for most catchments in the UK are in this range, 0.3 to 0.6. That's a natural, most catchments. If you are in chalk catchments or in and around North London, or South Oxfordshire, so you might be pushing up here. So these are very particular subset of catchments with chalk geology in there. And these are the kind of where you would think, well, doing rainfall runoff modeling in these catchments is difficult at all times because they don't react like normal catchments. It rains forever, but nothing ever happens because it just gets stored in the soil. So it's always difficult to do rainfall runoff modeling up here. And it turns out that just trying to enforce a response from an urban area doesn't work at all in this catchment, because all the sort of poor performing ones are up there. So that gave me even more hope that what we've done is the right thing to do for the majority of catchments. And if you were to study one of these high base flow catchment that's dominated by base flow, simple rainfall runoff models wasn't probably the way to go anyway. So that's where we ended it. A few years ago, the student left, went off to work for Southwest Water. Well, I think it's been quite an interesting journey. So if I look back, I think these models have been used. They've been used outside academia. RefH2 has become the industry standard. They've included in the SUDS manual. They've been used, this particular model here, has been used for water resources planning in Southwest Water. And we've used some of the same ideas to work with Acquia to think about how much water is intruding into broken sewer pipes in urban areas. And so I think I have found them useful as such. But I thought I would park them now, thinking onto something new. And so over the last few years, I think green-blue infrastructure has come up as something that I'm getting increasingly interested in. Managing storm runoff using nature-based solutions, and there's a whole raft of new people coming through in local councils and so who are very interested in nature-based solutions but have little to no knowledge about managing water at all. So I think there's an opportunity here, and that obviously links very strongly to multiple generations of people's work on SUDS. So I think there's strong links there, but I think there's some differences as well that we could be built on. And that's emphasis on the multiple benefits of nature-based solutions. And this is certainly, if you talk to people in the local authorities, and the messages they're getting from central government is that this is the key. Maybe if we think about SUDS, you think about managing stormwater and so, but actually economic pressures, more holistic thinking is forcing these people to think about, yes, sure, water is part of it, but people's well-being coming out of COVID, people with access to green space and so were managed better than others. Biodiversity crisis, we want to promote that. Air pollution is a big problem. People are getting sick from this stuff. Noise turns out is a big problem in urban areas. You would have thought, heating, etc., etc., etc. So people are looking for solutions that are managing, yes, water, but also a raft of other things at the same time. And I think as a community, we have a role to play here with our expertise, and they're crying out for our expertise. So just say a few things about what I've been involved in. So there was something called the Reclaim Network. I don't know if any of you have been involved, but this was a Network Plus UKI grant with Surrey, Bath, UK, CAs, Bangor, Warwick, where it's called Reclaiming Forgotten Cities, turning cities from vulnerable spaces to healthy places for people. And with lots of resources available in there, lots of activities. One of the things we were tasked to do was to do a literature review of the evidence in the literature, systematic review of the evidence in the literature on the effect of green-blue infrastructure on all these multiple benefits. And I was leading the water one. I still am leading the water one because I'm not finished yet. So we read through 50,000 abstracts, I'd say. We did the initial screen. There was more than 50,000 abstracts came up. I had to hire 8 undergrad students to help me read through and sort through all this material because it was too much for them. And lo and behold, I was given the search term, so there had to be nature-based solution, green-blue infrastructure. It didn't really involve SUDS. I think if I'd done that, it would have ballooned to hundreds of thousands. But of those 50,000, it boiled down to 41 unique studies reporting on green-blue infrastructure, where we could actually get data from. from 50,000 plus down to 50. This shows you the paucity of data and expertise out there on this. And the kind of studies that were recorded was grass, green roofs, permeable paving, rain gardens, road verges, and wetlands. And we looked through to try to figure out what are the evidence of reducing runoff volumes and peak flow. What evidence is available from these different intervention types. And grass, there's really not that much. It's 2 data points. That's enough to draw a box plot, though. So that's great. Whereas green roofs is obviously more interesting, easier perhaps, permeable paving, etc., etc. So we're still trying to finalize this. It's been a huge amount of work, but I think there'll be an interesting data set here. But I don't think this is the end of the story, in a sense that this is one of 7 big review studies, and the others review biodiversity, noise, air pollution, etc. So this is all coming into a big database that'll be available to local authorities to say they can look up green roofs and they can get a sense of how effective that will be and what benefits it'll bring. So it's a huge effort here. We've also done the same nature-based solutions in more detailed HEC-RAS models. We reviewed 600 odd studies on how people have implemented nature-based solutions into hydraulic models and tried to map the intervention types onto the governing equation. So I quite like this because this kind of feeds back to what I was talking about before, where you think about how the urbanization affect infiltration. Well, if you were to build a wetland or a forestation, so how would you represent all that stuff in a model? I find that quite interesting and an intellectual challenge, and lots of it has to do with changing the Manning's number. So the guidance is pretty rough, I'd say. And I think we still need, there's an S missing, it should be called the cost-benefit component of this. We're still just talking about the technical aspects, but decision makers need their, yes, they're interested in the technicalities, but if you start talking about Manning's numbers or infiltration rates, they'll glance over pretty quickly. And they want the cost-benefit ratios and how much is this going to cost and what am I going to save by doing this. So lots of work on the technical aspect, but I think this bit here, we're still missing. So I want to finish up with what we're doing at the moment. So at the moment, this Reclaim network we did was followed on by a UKRI-funded study called GP for Street. So it's greening practice for streets. So the idea is that you look at a typical street and you try to figure out what challenges, environmental challenges they're facing or might be facing under climate change. And then you prescribe, that's why it's GP, you prescribe some green solutions to rectify all these ills that you're facing here. So this is a consortium of 5 universities. We're in there. So looking at air quality, heating, runoff, that's me, well-being, and biodiversity. And we have some field sites, and one of the field sites is in Guildford, University of Surrey, and another one is in Bristol. That's the one I'm in charge of, and I think we're getting another one in Bath soon. And the idea is that we're going to focus on some green interventions in these urban areas, and then we're going to instrument the hell out of them, monitor everything we can, runoff, rainfall, soil moisture, biodiversity, air pollution, blah, 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 to try to capture some of these multiple benefits. So this is my postdoc, James. He's a very busy man. He's developed lots of low-cost soil moisture sensors that we buried inside this rose swale here to see how effective it is in capturing runoff from this road. So we've done lots of transects. We've only just implemented this, so we're still waiting for the results. But it's kind of an open invitation to say, if you're interested in this sort of stuff, we're trying to do it. If you have expertise, I'd like to talk to you. If you want to get involved, more than happy to talk to you about how that could be as well. Because I think this is, it's a great project. It's very complex. but I think we have the ear of the decision makers and the people in the local councils that are very interested in this. So this is my second to last slide. I'm coming to the end. So it's, yes, it's green infrastructure. It's trying to break up these impervious surfaces. And it is definitely to reduce runoff, but it's also to look at all these other aspects of the world we're living in and all these other people out there working on these aspects. So join us. So, the future modelling rainfall runoff in urban areas is difficult. I think monitoring it is very difficult. The information content we can currently draw out of urban land cover maps is limited. We don't distinguish between connected and unconnected urban areas, etc. I think there's lots that can be done there. I'd like to think that we could do something similar like we did with infiltration, but to think about how green infrastructure could be built into the model structures as well. And the idea would then be to take that forward into some tools that could be of practical use, so people can do their water calculations, and they would get more than just the peak flow out or the volume. They would get some more decision relevant variables such as multiple benefits and cost benefit analysis as well. That's it. I'll stop here. I hope that's I hope the timing was all right.
Yeah. Thank you. Any questions from the audience? Yes.
There are a point on the fourth or fifth slide is there are difficulties in field monitoring in urban catchment. So can you further explain what difficulties in monitor in urban catchment, especially for the large-scale studies? And second is, do you think the advances in techniques recently, such as the cheaper sensor, could help to overcome some certain difficulties to conduct monitor activities?
I can't find this slide you're thinking about, but thanks. I think that's a really great question, and I'm hoping I've come to the right place to ask ask for advice on this, because I've been involved in it a few times, tried, where we had. I think you could obviously monitor rainfall. That's not difficult. You just put up a rain gauge. I think it's the runoff component that's very difficult, because it's become quite diffuse in an urban area, and tiny changes in geometry, changes where the water goes, and so you almost have to crawl into the storm drains to implement to put the monitors in there. But it's dangerous, and it's a difficult job to do. So you might rely on the water companies, and they might do some of it. But my experience was that they did it for an extremely short period of time, and just to validate their models, their big models. So I don't think there were really. I haven't come across long-term monitoring of urban areas really, other than the ones I've been involved in myself. So I'm sure people who are more interested or more experts in sensors might have ideas here, and I have to confess ignorance as to where the state of the art of that is, even though I'm quite interested in where it is and if I can deploy it, because if I could, I most certainly would. I don't know if that answers your question.
Yes.
Other questions?
Yeah.
Anka?
Great stuff. I think I wonder, do you have any further thoughts about the incorporating the green infrastructure in the models? So one of the final point you mentioned. So the literature review you did, I mean, it's great stuff. Show a lot of different the performance. Different type of green infrastructure.
Yeah.
I wonder how could you implement this kind of knowledge in the logical modeling. Any further thoughts on this?
No, that's a really good question, and I'd say, let me just get this slide up here. Where was it? No, it's not that one. This one here. I feel I am The short answer is not yet, I think. I feel like I'm standing at the bottom of the mountain. I am where I was in 2000, at the beginning of the journey into impervious surfaces, in a sense, where you could come up with some very correction factors. I think this is what this is. You could say, if you implement a green roof, I don't know, 40, you just lower your runoff rate by 50%. That's it. But why does it, and how do I build this into the model structure? Is where I'm not quite there yet. So this is what we tried in the next step, where we then go, okay, well, which governing equations what in the physics change here? And so I think this is where I am with this. I don't have the answers yet, but I think there's an opportunity here.
Have you seen any papers on, the plant health, for example, considering, different, the health status of, the vegetation is in your review?
Yes, I have. Yes. So right now we're adding to this. So one thing that's not on here is trees.
Yeah.
So we're looking at trees and how that affects these things and what the literature says about this. And it's very interesting. I'm no expert in trees, but obviously depends what season you're in, whether you're in winter or summer, whether there are leaves on the trees or not, or whether it's a broadleaf tree or a pine tree with needles in, and that's a whole new raft of complexities coming up. I would like to build all this in, but I want to keep my modeling simple, because I'm also thinking about this is my background. There's a user community who don't understand all the complexities. It has to be simple as well as there's some challenges here. But
Thank you.
Thank you. I'm afraid we need to evacuate this room, so though Pete also put some comments on that. Thank you, but I think you might. When your train? Okay, then if you want to have a discussion with Thomas, you are more than welcome. Okay. Thank you very much for doing.